Well, we can start out. We got innocent off of the equator, which is good. You did you did something, Adam. Before you came on, innocent was rotated 90 degrees, and I was joking. He was on the equator, and that's my sense of humor, I suppose. So again, we have Adam Goad. Adam and I have worked together in Dr. Bayless's lab, and he's going to present you an overview of something called simulated annealing. One of the things about simulated annealing, I think you'll find, is that this shows and illustrates one of the important uses of noise and randomness in search. And randomness in search is all over the place. You wouldn't think it would be there, but it really has to work. So, Adam, I'm going to go ahead and turn it over to you and inform us, enlighten us, make us smarter.
All right. Well, thank you, Dr. Marks. Go ahead and share my screen. Let's see. Are you seeing the presentation view? Great. So yep, like Dr. Marks said, today we're going to be talking about simulated annealing. So what is simulated annealing and when might you want to use it? So if you're trying to optimize something in a multimodal search space, that's a search space where you have a high risk of falling into some kind of local optimum and then never being able to find the global optimum. Another way to look at this, a simple test to see if your search space is multimodal, is to see if your searches start location dependent. If you start in one corner, do you end at the same point as if you started in another corner? That would mean you're converging to the same optimum, and thus you probably only have that one. Well, it's a weak proof of that. It would be a stronger proof of having multimodality if you were to converge to different optimum. A common problem that simulated annealing is applied to, and is common throughout all optimization work even, is the traveling salesman problem. If you're not familiar with the problem, the idea behind it is that you have a salesman who's trying to travel around to different towns and different locations within these towns, and you want to find the shortest possible route for him to travel to save time and money. So the computational complexity of this problem, though, is big O of n factorial. So as soon as you have just a handful of destinations, this becomes far too large to solve exhaustively. On the side here, we have an image I took from a paper here that shows some different graphs of using simulated annealing to solve this problem, actually. Each of those, the vertices on those lines being one of the locations a salesman is trying to travel to. And we'll get into more about what the difference is between these plots later, but it's messing with the temperature of the annealing, which we will, again, describe more later. But you can see how this would be a problem where there would perhaps be lots of local minima when you're trying to get here. If you are trying to do some fine tuning and not changing your larger jumps, but you can easily get to a minimum there. But if you had moved those larger jumps, there might be an option that was an even shorter distance. So again, this is just a classical example of a problem simulated annealing is applied to. So what is simulated annealing? It's a method for adding noise to the search where you want to approximate the global optimization. So this is great for problems where you can't use a typical global optimization problem. So again, those problems that are multimodal, if we just use a gradient search method or just a hill climbing method, we would fall into the first optimum that we came across. We would never be able to escape that, and we'd be trapped there. But also for very large search spaces, things like the traveling salesman problem, where it's just infeasible to try and explore that exhaustively or something like that. This can allow us to kind of jump around more sporadically and fall into where we'd like to be. So it's named after the metallurgical process of annealing, which some of you might be familiar with. So that's where when tempering your steel or some product you have made out of metal, you heat it and cool it according to a precise schedule. And that's the same thing we're doing here. We are adjusting our temperature to adjust the amount of noise we're adding to our search. One example that Dr. Marks likes to use to describe this, I know, is if you imagine you have a bowl, and this bowl has lots of different dips into the bottom. There's lots of different little pools in the bottom of this bowl. And we dropped a BB into this bowl. It would fall into one of them. But if we started to shake the ball a bunch, it would jump around between them. And if we started shaking the ball less and less as we go, it will start falling into lower and lower optimums until hopefully it has fallen into the global minimum at the bottom of the ball. So how do we do this? What are we trying to design here, and how do we adjust this annealing to actually get what we want? Well, the first thing you have to do is to decide what is a neighbor. So as we proceed through our search, we're going to be checking neighboring points. In some cases, you might want to describe that as a point that is perhaps physically located within a mile if we're doing the traveling salesman problem. In the example I'm going to show here from our research, it is a one additional stub activated on our tuner. It's highly dependent on what your search is and what you're able to vary, but you need to be able to describe what it is and what classifies as a neighbor. So in the example I will show later, we'll see how how I tuned the neighbor parameter was allowing different distances to be selected. So perhaps something that was 5 states away could be considered a neighbor, or maybe only something that was 2 states away. Then once you have selected your neighbors, you need to figure out what your annealing schedule and temperature will be. So temperature is the time-dependent parameter here. So this is, you're going to vary it as your search goes, and it's going to affect how often a neighbor with reduced performance will be accepted. So this is kind of the how violently are we shaking that ball I described earlier. So, and then you have this annealing or cooling schedule that describes how you are changing that over time. A common example of this is the equation I've shown there, where it's simply 1 minus the ratio of how far along in the search you are, raised to some power there. One I've been using a lot is to the 1/10. But this is something that you'll have to design to match any kind of search you're doing. This is a good starting point, but to really get the most use out of simulated annealing, you're going to have to play around with all of these parameters a lot to get to where you want to be. And there's plenty of papers out there using different examples on different types of problems. And then the other big design parameter is going to be your acceptance probability. So given our temperature parameter there, what do we do when we measure a neighbor? If we, for instance, let's say that neighbor has better performance, in the examples I use here, I go ahead and accept that neighbor as my new point I want to be in. But if the neighbor has reduced performance, we still might want to accept that as somewhere for our search to go, so that we can jump out of those local optimums. This is what's allowing us to jump out of them. So if you see can you all see my mouse actually? Yes, great. So you see this equation here describes how we might go about accepting those. So if we have our performance at our previous state minus the performance at the current state here, give us that difference in performance, and then we divide that by the current temperature. And that will give us this, and then raise that to the exponential. That'll give us a probability. And then we will select a random number, 0 to 1, and we'll use that to determine if we're actually going to accept this state with reduced performance or not. And since temperature is decreasing as the search goes, this probability will become harder and harder to meet as we progress through time, again, showing us shaking that bowl less and less as we near the end of our search. So I've set up a simple example here to show this. Our search space is shown here on the left. It's the absolute value of the sinc function. We can see how there are several of these local optima on both sides, but one clear global maximum that we would want to get into if this was what we were trying to optimize over. So I'll play this video here. It'll show us moving along this using a stochastic hill climbing method. And we can see there, it was able to get out of both those local optima and find its way into the main global maximum here. So this is a very simplified stochastic hill climbing hill search I did here. I did not have it reduced step size. So that is why we don't see it zoom in to finally land at the end on that optimum. But we do see as the search went, it did hit that known value of 1 total optimum performance. So looking at the middle graph here, you see we have the blue line, the orange line, the yellow line, and the purple line. The blue line is showing all of our measurements, and in this case, it is mostly covered by the orange line. The orange line shows all the points we accepted. So we can see at the beginning of the search, when our temperature is higher, we're a lot hotter, we accepted every one, in fact, of the points that had reduced performance. We also, it wasn't that much of a change in performance, so that probability was a lot higher, and it was met each time. What we see as the search progresses and that difference in performance got greater, we did not accept those points that had reduced performance. So you can see here, the first 17 or so measurements, we were trapped inside the first local optimum. Then we got into the second before quickly getting into the global optimum itself. And we did hit the optima itself. You can see here the positions we were at over the search, and we actually hit it 4 times throughout the search. At the bottom left here, I describe the parameters that I mentioned previously. In this one, I did just a simple linear temperature example here. Just again, trying to show something very simple for this example here. So temperature just decreases linearly throughout the search from 1 to 0. The probability, that simple exponential I showed for when it was reduced performance, always accepting increased performance. And for neighbor ranged, I allowed X to vary to plus or minus 5. It would randomly select a neighbor from somewhere between 5 to the left or 5 to the right. And that is how we jumped through our search space here. That's how we were shaking the ball. Let's see if it will. Just the next slide. Great. So now a little bit on what specifically I've been using this for in research. So as the RF spectrum has become increasingly contested and congested, and more devices are brought online every day to try and use it, there's been several bands that used to be solely allocated for either scientific or military applications that are now having to be shared with consumer electronics. Specifically in this project, we're looking at the band from 24 to 48 gigahertz, which has now been allocated to 5G. But lots of this band previously were allocated to weather radiometry. So that's where we have these passive devices that are basically just listening to the atmosphere, trying to measure some of the quantum effects of oxygen, of the water molecules, stuff like that, that we are then able to determine how much moisture is in the air, the temperature of the air, stuff like that. We have both these systems that are ground-based and satellite-based. So to figure out how to get this 5G to coexist with these systems that can accept pretty much no interference with them, if there's any interference above the noise floor, it can affect the accuracy of the measurements and mess up the weather predictions. So we're taking kind of a 2-step approach to this. First, we're designing a spectral broker that's going to act as a kind of a traffic cop. It will accept requests from all of the 5G systems and all the weather radiometers, and it will say, okay, the radiometer over here wants to take its measurements now. So all of the 5G towers, I need you to not put any power in that direction. You can still transmit in the other directions, but not that one, and such like that. But then the 5G tower is now having to change its transmission characteristics. And this can cause issues for its RF power amplifiers. Their performance is highly dependent upon the characteristics that they're being used on. So as that change is required to not interfere with these radiometers, there is now a new optimal load impedance that we need to find in order to maintain our output power and range of these 5G towers. So working with Purdue University, they have designed us this new tuner, which we'll talk about more in a second, that allows us to quickly change that impedance that the amplifiers see to adapt and continue to maximize our system performance. So I won't go too much into the RF aspects of this, try to keep this more on the algorithmic level. But as I said, the RF power amplifiers, the performance is inherently different based off the impedance that they are shown. These impedances are typically represented on a Smith chart, similar to the one I've shown in the figure here. And so the performance would be dependent upon what point on this chart you have selected. And the optimal point will be moving as we use our broker here. So what this plot is showing is everywhere that the tuners that Purdue has designed can reach. The red and blue lines show, I guess first off, this tuner has multiple sections to it. The tuner consists of 2 cavities. Each cavity has 8 different stubs that can be activated. And the number of stubs that are activated determines where it is on this chart. So moving along the red lines shows that you've changed how many stubs are active in the first cavity. Moving on the blue lines shows you changed how many stubs are active in the second cavity. And what the squares represent is that one of those stubs actually has an analog device called a revactor on it, so that allows you to do some fine tuning. So you can get to one of those more coarse points, and then you can move around inside that box shown on the plot to get a finer solution and fully optimize that performance. But one of the big challenges with this is that we want to have a whole array of antennas here. 5G systems use MIMO, massive input, massive output. So they have large arrays that are all trying to transmit here. So we're going to have one of these impedance tuners on each of those array elements. The problem is that those array elements being so close to each other, they couple together. So what is happening at one of them will be impacting all the ones next to it, and actually all of the ones in the array, but mostly it will affect the ones closest to it. So our search space is going to be changing underneath us with each step we take. If you change tuner 1, tuner 5 is no longer performing the same way since it has now a different impedance it's showing. I will show some results here of experiments performed with and without this coupling. So a bit more on this search space that we're going to be working in here. Again, I mentioned it has both that discrete digital component as well as that analog continuous component. We're only going to be looking into the discrete area here for this simulated annealing and this presentation as a whole. So again, we mentioned earlier about how you have to find those meaningful neighbors. So if we just laid this out as a grid of how many stubs do you have active on each of those cavities, 0 to 7. On the first cavity, you could move along this axis. On the second cavity, you can move along this axis, perhaps. And you would get all of these different intersections, these being all the points that you could access with the tuner. And then if I play this video here, we can see how this morphs into our physical search space, being those impedances seen on the Smith chart from the last slide. So how should we select our neighbors? Should we select them based off where they were in this digital search space, or should we select them where they are in our physical search space? I've investigated both methods a little bit, but I'm currently going with how they are in this search space. It is a lot simpler to implement. It's very intuitive to do. And I did not see much performance improvement coming from trying to do it based off distance from each other in this plot. So if you were in a point up here, you would have lots of neighbors. As the point down here would only have these 4 neighbors, perhaps, if we could even get a range measurement that would select those. So yeah, that's a bit more on how the search space is. And since we are considering a 16 element array, and each of those elements has those 2 cavities, like I mentioned, that makes this a 32-dimensional discrete search space. And I'm sure Dr. Marks has mentioned the curse of dimensionality to you, and we are very much impacted by that here. I thought I had the number, but I think it is somewhere around 2 billion, if not more. No, it was a lot more. I think it was 2 to the times 10 to the 17th or something like that, possible states that this search could be, and it is far beyond our abilities to test exhaustively. So then, how did simulated annealing actually perform on this problem? First, we'll look at some results without coupling. The reason I wanted to look at these is to show some of the algorithmic use here, because without coupling, we can predict the known optimum performance, since it is just the summation of the individual performances, and we can find the optimal performance of each one individually a lot easier, because that is just 16 two-dimensional searches as opposed to the 32-dimensional search. But in this case, I still ran the algorithm as if it were the 32-dimensional search, but we just were able to look ahead and know what the best answer is. So here I did 500 measurements. And again, that's 500 measurements over that super large, several dozens of orders of magnitude search space. So that's a very small number of measurements considering that. And I was able to get within 0.1 these are dB of gain here, actually, of performance. So that's an amount that we'd usually be able to attribute just to noise and measurements even. So this search did very well. I used the temperature schedule, similar to the ones I showed previously, but I did a to the power of 1/10 here. So we cooled off. We started at a low temperature and cooled off rather quickly, actually, before towards the end there it was very flat. And you can see that here at the beginning, we accepted lots of losses in performance down here. But as we went, there were fewer and fewer of them until in the last 2/5 here almost of the search, it doesn't appear to have selected any decreases in performance. And I allowed a neighbor range on that digital graph of ±4 with the same probability of acceptance we showed previously. So this is an example where simulated annealing did very well, in my opinion, at least. So then, well, you would probably ask the next question of how does that compare to not using simulated annealing? So this is the exact same problem setup, except I set the probability of accepting a case where there was a decrease in performance to 0. So it wouldn't try to shake the ball at all. It'll just go up as it can. And we can see it has a very similar shape to the plot there, but it clearly got caught in a different optimum here. It had about a half a dB, 1/2 to 0.6 dB performance decrease compared to the with simulated annealing. Now that might not look like much in this example, but still that shows the use of the annealing, and that is, like I mentioned earlier, this is a multimodal problem, so that is start position dependent. So if I had chosen a different starting parameter, we could have seen much worse results there. I had some states that would end up with around a performance being at about 13 or so there, as opposed to all the way up in the range of 20 like we see here. So then another thing to look at is how actually varying those parameters does things. So on the left here, I did just to the power of 1/1. So this is just a linear decrease in temperature as opposed to this 10th root decrease in temperature. So this is like the simple example I showed earlier. And you can see how there is much more noise added to this search. We are accepting decreases in performance almost all the way out to the very end. And you can see that it wasn't able to go into any optimum really. It kept being shaken out of each of the optimums. It was never able to really vest into one of them and kind of even reach one of the local optimums even. It did find a decent point around the beginning and the middle though of around 19.5, but still compared to what we were able to get using a better designed annealing schedule, it is not good. So what this goes to show is when you are trying to use simulated annealing, you really have to work with the problem and try to figure out what your parameters should be. There's a lot of papers discussed really. What I could find is there's some suggestions on how to start with these parameters, but really it is just a matter of playing with them and applying your domain expertise to try and figure out what is the best way to tune these parameters for your search space. So here's a result of actually doing it with that coupling I mentioned. So again, we are not able to know the global optimum here, so we can't truly know exactly how well this search did, but it seems to perform very similarly to the examples without the coupling. We can see the annealing at work here once again, jumping us out of local optima as we go. And we got a little less than 20 in our performance this time. But again, we can't know. Maybe that is near the best here, or since we don't know the best, it is a lot harder to actually tune those parameters here. Moving forward, I will actually be doing this using RF and electromagnetic models. All these simulations were performed in MATLAB using a large number of simplifications, which is why we are not yet ready to publish this work. We want to get some better simulation data as well as some real measurements, hopefully in the near future. So it's really hard to try to tune for this search when we know that we're going to be adapting later to a more exact environment. But this shows a lot of promise, I think. And again, this is the same search parameters that were done with the other one. It's just adding that coupling in, creating that dependence between all those optimization dimensions, greatly increasing the complexity. Oh, and it looks like I did not put the long list of references I had in here, but I will do that before I send the slides to Dr. Marks, who I believe is intending to send all these slides out to the rest of you.
Yes.
So you may reference them as you wish. Do we have any questions? I suppose?
Yeah, does anybody have any questions?
I have a quick question, Adam.
Yes,
First of all, great presentation. That's kind of an interesting use case.
thank you.
I was kind of curious, did you try to compare this against like, so your search space was discrete, right?
Yes, we are only considering the discrete part of the search here, yes.
Okay, so it's like a discrete input and then continuous output for the most part?
So yeah, we have to choose 32 numbers, 0 to 7, and then yeah, we get a continuous output from there, yeah.
Okay, like is there some known like relationship, like is this function approximately linear or convex in some case?
Right, so are you familiar with RF at all?
No, unfortunately.
Okay. Well, when you have a nonlinear device, like we are, so these actually examples were done on a linear device, I suppose. We'll talk about that. So then on this Smith chart here, the performance of that device, there will be an optimum location, and then contours will fall out from that. If you're familiar with the geometry concept of circles of Apollonius, that is actually how I modeled them here. So it's circles whose centers lie upon a linear line coming from that optimum location. So it is, yes, it is convex on each one of these individual two-dimensional search spaces. But I suppose I haven't gone to prove if it is in the 32-dimensional search yet. I would suspect that it is, though.
I would suspect that your results suggest that the search space is indeed multimodal, right?
Yes, it is multimodal.
Yeah,
So
there's no
multimodal
question.
means non-convex. Yeah.
Yeah, so you keep on falling into these different minima without the use of simulated annealing. So, yeah, definitely, it's a very complex, hilly sort of a search space, of a landscape, of a search landscape. See, one of the problems that you have in these things is sometimes you don't have the wherewithal to understand the model. Many times we have a model, that the search space is linear or convex or something like that. And remember, the more information that we can put into the search, the better. And what we're discovering here, just by playing around with the search, that there's an enormous number of these minima. So we have to be very careful in the manner that we perform the search.
Yes, exactly.
I think also some of the things that Adam's presentation points out is the importance of parameter choice in search. Every search algorithm has choices of parameters that the engineer must apply. And indeed, all design is an iterative process. You try something else, et cetera, et cetera. And eventually, the more domain expertise in general that you have, the quicker that you come to an acceptable design. But again, there was the parameter choice here. On the left, he did the linear decrease in temperature. On the right, I don't know what that is. That's kind of that reminds me of a charging up capacitor or something, right? No, a discharging capacitor. It's kind of an e to the minus x curve in a way, isn't that?
Yes, it's a 10th root. Yeah, it's a 10th root decay, I guess you could say.
Yeah. Okay. So, well, no, it's not an e to the minus. I don't know what it is, but the one on the right is much more gradual than the one on the left. The one on the left is doing things too fast. One of the things I like to mention in annealing is that as Adam mentioned, it's used in metallurgy. And one of the great examples is the cooling of ice. If you have water and you cool water and you decrease the temperature too much, as on the left, you come up with ice with all this cracks and stuff in it. On the other hand, if you decrease the temperature very slowly, the ice will come out nice and clear. And we've all seen cracked ice and we've all seen clear ice. It's not metallurgy. It's not a metal, but the phenomenon is apparent there. So yeah, your choice of parameters is incredibly important. There was some classic work done by a couple of people called Gieman and Gieman. I can't generate the exact results, but they showed that if in certain cases, if you decrease the temperature slowly enough, you went into a global optimum. You were assured that you were not stuck in a global optimum. The problem with this is that the number of iterations for the decrease in temperature that they proposed generally approach what you would need, the number of iterations you would need to do an exhaustive search. Because you can always find the optimum, right? If you could do an exhaustive search across your entire space. And by the way, that's something to always remember. Don't apply search algorithms if you don't need it. Some search problems are such that you can do an exhaustive search. Just try every possibility. Turn on your computer, let it run for 2 or 3 days or whatever, and you know that you get the exact result. Now, that's not something you can use in real time, but if you're trying to do something in a design, that's something that can be done, as opposed to kind of a iterative updating, tuning sort of thing where time becomes of the essence. So yeah, this was very good, Adam. That was very good. Appreciate it. Any other questions?
I have a quick question.
Sure.
Yes.
I'm just trying to get my head around the physical side behind it, because I think some of it would have to do with where my research would be heading. But if I'm understanding correctly, is it like, so you have an array of antennas, is that right? Antenna elements, foil elements?
Right. So we have an antenna array. We're considering 16 elements here. And on each of those antennas, we've placed one of these tuners and a power amplifier.
Okay, gotcha. And what you're changing, but you're varying, is the impedance tune, like
Yes.
tuning the impedance. Okay. Very
So,
cool.
so here's one way to think about it. I think I've mentioned stochastic hill climbing, and Adam mentioned it briefly. I was probably remiss not to elaborate on it. But in this case, Adam, how many parameters do we have totally in the array? I forget.
Well, we have 16 elements, so it's a 32-dimensional space.
32-dimensional space, but each of those elements itself has certain parameters, don't they?
So yeah, each element has 7 digital stubs, and it's the number of stubs that is active that we care about.
Yeah, so we got all of these elements, each with 7 individual stubs, and we want to, each one of these can be thought of as a knob, and we have to tune the knobs so that we get the optimal performance. The beautiful thing is if we get a knob setting, we can figure out what the performance is. That's what those curves that Adam showed were. So how do you do that? Well, if you did specific hill climbing, you would choose one of these parameters at random, do a little tweak, and look and see whether or not your performance got better. If the performance got better, whoop, you took a step in that direction, right? If it got worse, you don't want to go in that direction. You go back to where you were and change one of the other parameters and see if you got better. And you keep on doing that one at a time. Now that's without annealing. Now what Adam did, and Adam, you're going to have to correct me if I'm wrong. You had actually, sometimes it got worse. And what the noise does is it says that if it gets worse, you keep that worse if you have noise, if your temperature is high and you're shaking the bowl a lot. So you get worse, but getting the worse is okay in the beginning with a certain probability. And then keeping the worst, that probability decreases as a function of time. And eventually you're not keeping any of the getting worse. You're only keeping the getting better. And I think that's the way you did it. Is that right, Adam?
Exactly. So you can see on the blue line here, there were lots of points that had even worse performance. But even at the beginning, we didn't accept those just with the probabilities there. But then yes, as we go throughout the search, you can see towards the end here, just visually inspecting, I don't see anywhere where it selected a lower performance.
Okay, point out a place where it got a lower performance. Okay, I think the orange curve
Yes.
kind of follows. You can see the orange curve, and that orange curve really in the beginning really dips down. We're accepting a lot of false steps going downhill. That's okay. But
Yeah, anywhere the orange curve has dipped below the yellow line is a point where we've accepted a decrease in performance.
yes, and there is a subtlety there. There is a yellow line and the orange line. So I guess what the yellow line is just what the best performance is so far. Is that right?
Yes, that's best performance so far.
Okay, and the orange line, which is jagged, which is below it, is the result of either accepting going uphill or downhill or not. And you can see in the beginning, we make a lot more mistakes. We accept a lot more downhill. So the optimization actually goes downhill. Why? Because we're shaking the bowl a lot, as Adam talked about. And then of course, temperature means lots of movement, right? Lots of vibration. If you have a high temperature, your molecules are really boogieing around. And as time goes by, you begin to cool it and shake the bowl less. And this is exactly what's happening here as the orange curve begins to go up, and you see fewer dips, but you do see them there. I see some dips around between 200 and 300. Yeah, point those out.
Yeah.
Yes. And so there's still, a probability enough that if you step downhill and you get worse, you say, yeah, I know I got worse, but I'm going to accept that because I'm doing simulated annealing. But the probability of accepting getting worse reduces to be a smaller and smaller number as you increase, because that probability corresponding to temperature has decreased. Does that help, Matthew?
Yeah, that makes a lot of sense. So just a quick other question. Your performance is you're calculating or predicting the signal to noise ratio and thus bit rate of those antennas? Or are you running?
Actually, no. My performance here is a sum of gain, actually.
Oh, okay.
Mhm.
So you're just talking about how powerful the antennas are, like the
Yes.
gain.
Yeah.
Okay.
Mhm.
And you mentioned this model is summing them individually. So you're not taking into account mutual impedance effects and stuff like that yet?
Right. So in the without coupling results, I did not, so that I wouldn't be able to know my true optimum. But I have looked at it as well with accounting for the mutual impedance, the mutual coupling.
Okay, that's interesting. So the purple line here, which is the one on the top, is that just your empirical result, or is that the theoretical best?
That's where the search ended. That's the best the search got.
Okay, so what Adam did, let me they say that learning is spaced repetition. So let me go ahead and repeat that. See, in the other cases that he first of all presented, we could actually figure out what the best result was. We knew the gold standard. We knew it was the top line there. And we knew that that's the performance we would like to achieve. But as we get into this mutual coupling, it's very difficult, I don't know, maybe even possible to figure out what the optimal performance is. So you just do the best you possibly can. So that's with the other curve that Adam showed. Can you show that, Adam, the other curve? Yeah, it's that one.
This one, yeah.
We don't know how close that is to optimum, but we have experience with the other simulated annealing that, it's working pretty good. And maybe if we don't know this is right, maybe mess around with the annealing schedule, how quick we lower the temperature as a function of time, and see if the results change. We might be stuck in a local minima here. This is one thing you always have to remember. Unless you do an exhaustive search, you are never, ever, ever 100% sure you're at the global maximum. You're never sure. And so the best we can do is to bring in our domain expertise and apply these algorithms and, mess around with them a little bit and tweak them a little bit to get better and worse results. And then finally choose the search parameters that give you the best result and say, hey, that's it. And again, as engineers, we're typically not interested in global maximization. Rather, we would like it to work well, but often, typically, we are given a performance criterion, a standard, if you will. The military has all sorts of standards for everything you buy, from electronics to toilet paper. They have something called mil specs, military specifications. And so we would like to meet that specification. In this case, we would like it to be optimum, but we know that unless we do an exhaustive search, we can't do that. So we want to do everything that we can in development of this search to be assured that we get the best result that we possibly can, or a really, really good result.
Mhm.
Any other questions?
Can I make a sort of a quick comment on this is sort of more of a computer sciencey and quantum computing relation,
Sure.
but in the field of quantum computing and classical computing, you can do quantum annealing or classical annealing, which is
Yes.
kind of like what you're doing here. And it's actually analytically possible to compute the optimal annealing period for a given problem. Unfortunately, computing that is just as hard as solving the actual problem. But there's, in the case of like in the quantum world, everything is linear, and the complex version of symmetric called Hermitian. It basically makes your problem a little bit easier in the sort of classical sense. Like your problem has like 7 different settings for each of your 32 dimensions that you're trying to tweak. Essentially, you can model that as a giant, what would that be? 7 to the 32 by 7 to the 32 stochastic linear matrix. And you can compute.
It's 8 because you got 0, but yeah, it's
okay.
a giant hypercube, I believe. Yeah.
Yeah. If you were to theoretically able to compute the Jordan canonical form and find the what's called the spectral gap between the principal eigenvalue, which is going to be 1, and the next eigenvalue less than 1, the optimal temperature is actually proportional to 1 over that spectral gap.
Well, does that, if you're talking about eigenvalues and eigenvectors, you're inherently assuming a linear sort of problem, you know, that can be placed in a matrix form. And
right.
I believe many of the problems that we're going to address are unlike that. I would also point out that I mentioned Gieman and Gieman, their original classic paper. If I recall right, they do something similar with regular annealing, the ability to find out an annealing schedule that works. But again, in that case, it borders on exhaustive search. And so, so yeah, I guess I'm not surprised at some of those things. Any other questions or comments? Okay, how do we applaud just to do this? Or, you know, in Germany, what they do, I used to go to Germany every once in a while, and they clap by pounding the table. So they have a tabletop and they go boom, 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 boom. So everybody stands around, and instead of applauding, they go. But in America, for some reason, we put our hands together. And by the way, did you know that you can make your applause much more louder? I'm going to give you clapping lessons now. Are you ready? You can clap like this. I don't know if you can hear it. If you cup your hands, you can make a booming clap. So if you're really enthusiastic about a performance, cup your hands. Let the person know. If you're moderately impressed, you know, or just like some of the petite people do, you know, just kind of like that. Okay. Thank you, Adam. I think you have to race off to class, right?
Yep, I have to go get to my own class now. But yes, if anyone has any more questions or want to talk about simulated annealing and maybe applying it to their research or anything, feel free to email me.
Great. Thank you. Thank you very much. And you'll send me those slides and I'll make them available to people then.
Yes.
Okay. Excellent. Excellent. Okay. Thank you. Bye-bye.
Thank you.
Bye-bye. Okay, let's continue. That's interesting, isn't it? Simulated annealing and the use of noise in order to perform optimization. And we see the use of noise extensively in optimization. We see it, like, for example, in evolutionary programming, where we said that there were the repeated operations of what? Mutation, survival of the fittest, and then repopulation. And that mutation is stochastic. You have to figure out where to mutate. And that itself is a stochastic process. And I think that just in about, well, in many, many, many algorithms that you can indeed, well, many search algorithms and training methods in artificial intelligence require something stochastic. There are some that don't, but I think a lot of them do. Okay, let me go ahead now and switch the subject. And we were going to very quickly talk about deep learning. And I'm presenting it in a way which is maybe a little bit different than some of you have seen. Okay, so where is my PowerPoint? Okay, I'm just going to share my screen and put the PowerPoint up here. And I was having problems with this before. Let's see if this is a recurrent problem. We'll find out. We talked about the use of correlation, and correlation is used extensively, even in your cell phones, for decoding messages that are corrupted by noise. And I believe that they use a space of 11 Barker code in order to do that. Barker codes are also used in radar because radar uses matched filtering. Also, you send out a ping and it comes back and you have to do a correlation with what you sent with what you get in order to figure out where there's a big peak. And there's going to be a delay of what you sent coming back. So that occurrence of the big of the return signal is going to dictate how far away that your target was. And that is done using kind of a matched filtering or a correlation sort of thing. I wanted to talk about edge detection. You know that here, what we did is we ran a window. Okay, where's my cursor? There's my cursor. My cursor is white. I can't use white on a black background, but I can use red everywhere. So what happened is that down here, when we had our noised up version, we took a little window here and we put in our Barker code. I forget what it looks like, but we put in our Barker code and we slid this window across, and we did this inner product, the sum of the product at every point. So we did the sum of the product here, we slid it over here, we slid it over here, you know, eventually we work our way down here, and we did the sum of the product in each one of these points. Doing the sum of the products with the noisy signal gets us the result that we show on the right. And you can see when the signal lines up very well with the kernel, what we coded it with, that you get a very, very nice peak. So let me talk quickly about edge detection. This is something that we can use very trivially on edge detection. And my computer is screwed up again, so I don't care, because I know what to do. I want to talk about edge detection, but I'm going to just talk about it in terms of the derivative. What do you do with a derivative? If you look back at calculus, what do you do? If you want the derivative of this curve, this x of t, you take this point minus this point, and you divide by the separation, right? So it's kind of the x of t plus del minus x of t divided by del. And you take the limit of that as del goes to 0, and you have the derivative, correct? Now let me give you a problem. This is a very interesting problem. What is the derivative of n squared? It's equal to 2n, is that right? Everybody happy with that? But it's also equal to d times d sub n of n times n, is that right? yes, which is equal to d sub n of n plus n plus n, and there's n of these, right? Aren't they exactly the same? Do you agree with that? Nod if you agree. Okay. So what's the derivative of the first one? It's 1 plus 1 plus 1 plus 1. But that's equal to n. So what we've just shown in this example is that 2n must be equal to n, right? So there's obviously I did some trickery here, but this is one of the most interesting problems that apparently looks like a paradox, but has an interesting resolution. You think about it, and then I'll explain the paradox in a minute. Let's go back to this idea of computing a derivative. If we have a signal here, and say the signal has some abrupt edges. What would happen if we took a window, not like the Barker code, but we took a simple window that looked like this? And so we were going to slide this window across this function x of t at every point. I think you can see that where it's kind of a constant here, this is kind of a constant in this area. It's not exactly a constant, but it would be this first part minus the second part. So we get something like 0, wouldn't we? Where it becomes large is when we get to one of these discontinuities, right? If we get to one of these discontinuities, we're going to have a big negative minus a big positive, right? We're going to have this part minus this part. And as we go across here and do our correlation, we're going to have a big spike there, correct? And then we're going to get some other stuff. It looks like it's negative here, but not much is happening. Then we come over here and we get a big spike, right? So we see that the derivative can be approximated in an edge detection sort of way by this positive value minus the negative value, right? And that can be done by a sliding window. So this would be a good way to detect edges or abrupt discontinuities in one-dimensional functions. That's good. Now, if you've had a course from Dr. Schubert in image processing, you're familiar with the generalization of this idea to 2 dimensions. And this is, for example, when we're trying to locate an image, we're trying to locate an image in a picture. Now, I am going to escape from the presentation mode for reasons which I hope become apparent here. And my PowerPoint has slipped off the screen here. Okay, so what you might want to do is detect this tank in this picture. And how would you do it? Very similar fashion. You would take this tank and you would move it across, just like we did in the Barker code. And eventually we would get to the point where, okay, we take the sum of the product of the pixels, sum of the product of the pixels, sum of the product of the pixels. But eventually we would get here and we would go, whoa, the sum of the product of the pixels just got really, really high. So we would put a little dot with whatever point we were talking about in terms of moving this tank. And we would say there is a tank there because there is a high correlation of the image with the tank. So this is an example of, kind of using not a Barker code, but an image processing of how we might do this. Now, there's problems associated with it, but I hope you can see the idea. This idea of sliding windows is very, very powerful. I mentioned Dr. Schubert. No, it's the next one that I think that would be in Dr. Schubert's domain. This is something called the Sobel operator. This is a two-dimensional equivalent of computing that derivative, you know, where you were positive in the window and then you were negative in the window. And this is something, this is a window which you can slide across an image, and in doing so, detect edges. And can you see what happens here? We have big numbers here, and we have negative numbers here. So it's a lot like the thing that we saw before. You know, it's a two-dimensional representation of that window that looks like this, right? It was positive on one side, it was negative on the other side. So this window, if we slid it across the window, if we slid it across the image and did correlation, would detect vertical edges, correct? And the window on the right in this Sobel operator would generate horizontal images. Sorry, horizontal edges. And here's a simple example. This is an example from, okay, I gotta stop again, I know. Takes me 4 clicks to reboot. This is an example of a picture on the left. This is no biggie. I think I lifted this from Wikipedia, where you had an image and you applied a Sobel operator to it in order to detect the edges. And so this window just slid across the image that we have here on the left. And as a result, we generated the image that we have on the right. So it was an edge detector. So we see this idea of sliding windows being applicable in many cases, in correlation for image, for object detection in an image. We see it in edge detection also. Now, all of these are fixed, and that's all well and good, but why do we choose these? Why don't we look at images and instead don't figure out that there's a +1 here and a 0 here and a -1 here, but figure out something which allows us to identify these images where this might be 1/2 and this might be 2/3 or something like that. And these are not chosen by human beings, but they're rather learned by what you're trying to suck out of the image. This is the basic idea behind so-called convolutional neural networks, which should be called correlation neural networks. So here we have a case. Suppose there's a 3x3 window sliding across a picture of me here. Okay. And what we're going to do now is we are going to train these weights. Now, what are these weights? I got to change the color because it went back to. Okay, what are these weights? These weights are going to be weights that we're going to learn, just like in a neural network. So this might be weight 1, weight 1, 2, corresponding to, let's see, I guess I don't want to do that. I guess we could literally name these 1, 1, 1, 2, kind of like in a matrix, 1, 3, 2, 1, 2, 2. So we could call this one weight 1, 1. This one would be called weight 1, 2, and this one would be weight 1, 3. And what we want to do instead of fixing these weights is we want to place this in a neural network so that we are able to learn what these weights are in order to behoove us. And that's what happens in convolutional neural networks, or correlation neural networks, I should say. So here is what we have. We have an input, and say we're trying to differentiate between cows and dogs, or basketball players and sumo wrestlers, or whatever. We start with an image, and now we have this little window here. We have this window, and we would like to figure out the numbers in this window that would collapse down to a single point, right? This would be the correlation. So this would be a window, and this would be the correlation. And we're actually going to choose a bunch of windows. We're going to choose another window here and another window here. And these are referred to in this example as a feature map. So we have a number of different windows that we are going to train, and we are going to learn what those interconnections are. Well, it turns out, if you know, every time you convolve, you make things bigger, and well, maybe things are too big. So what we do in the second version is there's a process which is typically used called pooling. So a group of pixels in this image are actually aggregated. Now, how do you aggregate? A lot of them do max. They take the maximum of the result in here, but you know, I've seen it where they do an average or other aggregation, and they take this, say 3x3, I'm making that up, this 3x3, and they condense it into a single picture. And you can see that this picture is a lot smaller than this picture. But again, it is these values in the window or in this little correlation window that we are learning. Now, what do we do again? Well, we choose another window, and we want to learn the values in this kernel that is going across. So we do another correlation here. So we do another correlation, and that's going to generate another image. Now there's going to be a different image for each one of the windows that is used. So we're going to have a number of feature maps, and then we're going to pool it again. And we can go through this a whole bunch of times and have different layers of the deep convolutional neural network. What is interesting is that in most of the applications, do you know what this first layer does? We learn these weights, by the way, using error back propagation, just like we did before. We use error back propagation. But you know what the first layer does generally? It usually does edge detection. It trains itself to do an edge detection. So we have all of these edges, and each one might be edge detection for like a different feature. And then these features begin to be combined in these other layers, and eventually you emphasize what you're looking for and discard what you're not looking for. Then this goes for a number of different layers. Then it goes to a traditional neural network. This is a very typical architecture. So it goes to a traditional neural network like we talked about before, where there was no convolution happening. And then they're combined in order to give a generated output. So this is the idea. Now, I want you to notice, and this is the thing that astonished me about convolutional neural networks. You remember we used to have the curse of dimensionality, and the curse of dimensionality here was that we might have, I don't know, say, if we had 100 by 100, we would have 10 to the 4th pixels. That would correspond to 10 to the 4th inputs, right? If we used a conventional neural network. And that 10 to the 4th inputs would require an enormous amount of training data, wouldn't it? Do you remember the curse of dimensionality, how it increased? Well, the beauty of convolutional neural networks is that this curse of dimensionality is mitigated by only requiring not the training of all of the inputs, but only, for example, a 3x3 sliding window. That's all we have to learn of those results. So this is the basic idea behind the deep convolutional neural networks. And when they came out, this was the first time where we could use entire images to train a neural network, whereas we couldn't before. Previously, before the convolutional neural network, if we wanted to train between sumo wrestlers and basketball players, we couldn't put the pictures in. Rather, what we had to do is we had to do feature extraction. We had to figure out, well, what's important? Probably the weight and the height. So we took all that, we didn't use the picture, we just used the weight and the height in order to differentiate between sumo wrestlers and basketball players. Now we can put the entire image of sumo wrestlers and basketball players in and learn them using this deep convolutional neural network. So it became much more powerful. And again, it has tamed the curse of dimensionality because we don't have to train for 10 to the fourth pixels. We're only training for these pixels. So right here, I have a single input. This single input, okay, can I talk and click at the same time? I don't think so. The single input can actually be generalized to higher outputs. For example, suppose you have a color image. Well, that's okay, because with the color image, you can have 3 different layers here, like red, green, and blue. And now your sliding window is going to be a little cube, if you will, or at least a rectangular box. And you're going to learn all of the elements in this little rectangular box as it does the correlation in this 3-dimensional result. And again, we get different results. It's kind of interesting. I just wonder if time goes on, whether we're just totally going to erase history and redefine convolution as correlation. I don't know. But here now, as we go into different layers, we are going to get different maps, for example, in layers of 3. And we will do poolings in layers of 3. And here they're using max pooling, which means that they look at a specific little square, and there's a number of numbers in there, and they just use the maximum. They throw away the rest of it, and that makes it to the next layer. So that is the fundamental idea of convolutional neural networks. Again, it's trained exactly the way that the regular neural network is trained, and uses error back propagation as its default in almost all cases that I'm aware of, and it works incredibly well. Also, you'll see that the number of interconnects and the number of things going on here is enormously large. So you remember that property of error back propagation, where according to Hebb's law, in order to update a weight, you only needed to know what happens on both sides of the interconnect. That becomes more and more important here with deep convolutional neural networks, especially as you get to more and more layers. And that property is going to increase your computational overhead as opposed to other training algorithms and search algorithms that perform this operation. Okay. Now, you remember we talked about the autoencoder. On the top here is just a scaled version of the image on the previous page. We can also do deep convolutional autoencoders. Remember what the autoencoder does? That's where the input matched the output. It was trained to be exactly the same thing. So there are convolutional neural network autoencoders. And by the way, here you can see the explicit 3 layers of an image, which is the red, green, and blue, if that's the way you want to define your image. And so it comes down, and the smallest value here is called the latent space. Okay, so we can perform convolutional neural network autoencoders also. So that basically completes the neural network lecture. Again, if you're more interested in this, I would suggest taking the course by Dr. Rivas in computer science or Dr. Dong in electrical engineering that is more interested in the applications of this. In computational intelligence, we have a much broader scope. We need to get through fuzzy logic. We go through swarm intelligence and some of the other interesting things. So that's it. Now, what we'll do next time, there's another really cool application called GANs, Generative Adversarial Networks. You've heard of deep fakes, and deep fakes are, astonishing. There's a bunch of cool websites. And I think I talked about one, thispersondoesnotexist.com, for example, where they generated pictures that really, really look like people. So next time we get together, I'm asking Glauco Amigo to come in and give a lecture on the way that these GANs work. And interestingly, you know, the autoencoder has the encoder and the decoder, and the GAN kind of uses the decoder part of the autoencoder in order to generate very interesting results. And Glauco will go through that next time. Then after that, I've invited Justin Bowie, who is more of a what's the word I was, savvy than I am, to come in and talk about some of the resources that exist on the web for using these neural networks. It turns out that for some reason, there is Google, for example, has released all of their very powerful artificial neural network software, and it's available for free, and you know, everybody uses it. And what are those, you know, what are those tools, and how do we access them, and how do we use them? So Justin Bowie just got his PhD, is going to be talking to us about that. In a similar fashion, one of the things that motivated things like deep convolutional neural networks and the latest resurgence in artificial intelligence was the increase in computational power, number one, and the increased availability of data. We have data coming out our noses and our ears these days. And that just allows us to do a lot of interesting things because we have all of this information that now we can process. So that concludes my my lecture, and you've learned today about what Justin Bowie did, which was simulated annealing. Maybe someday you'll come along and do some simulated annealing. Maybe you'll never touch it again in your life. But one of the purposes of graduate courses is just to increase your tool chest. And maybe in 5 years, you'll come along and said, oh, I remember, what was that? What was that? It simulated something, annealing. Oh, I remember that. That looks applicable to here. And you can go back and you can dig it out of your toolbox. Okay, any final comments? Okay, thank you very much. We'll see you next time. Be of good cheer.